Welcome to Topcast, the penultimate beginning of infinity episode. And last time we summarised a lot of the themes that are in The End of Science by John Horgan and contrasted it with the vision that we are given of science and knowledge by David Deutsch in The Beginning of Infinity. And I think I concluded there with some of my own favourite reasons why we should think this is not the end of science at all. That there are so many really interesting, unanswered questions right now that we are on the precipice, we're always on the precipice, but on the precipice of yet another bunch of grand fundamental discoveries in physics. Now, this idea that we are at the very beginning of infinity, the beginning of discovery in science, that there are just so many things we don't know, has been borne in upon me in a really fortunate way, because presently my job involves almost daily conversations with physicists working in very fundamental areas of theoretical physics to ask them about what areas of physics need additional attention. Just today, I was speaking to a very accomplished physicist working on the question of fine-tuning. This is a huge open question. Why is it that the constants of nature and the laws are just such that we get complex chemistry in our universe? Could it have been otherwise? Well, in speaking to this person, yes, indeed, it could have been otherwise. And there's a really interesting set of possible solutions, but really none of them seem viable at the moment. Another route is, of course, Chiara and David's constructor theory, which might give a new lens through which we can view this problem and perhaps find solutions as well. And this is just within theoretical physics, just theoretical physics. Never mind biology and all the open questions we have there. How could anyone think we're at nearly the end of science when something like the coronavirus has just ravaged the world? I don't know. There will always be more problems. Even if the fundamental physics theory could be found beyond the standard model, beyond quantum theory, and we stopped there, I don't think that's the case. But grant that for argument's sake, there would still be scientific problems to solve. Every single physical problem that we encounter, asteroids from the sky, volcanoes from the earth, viruses from the sea, and who knows where else, are going to require scientists to address them. So it's not possible to reach the end of science unless we reach an unproblematic state, which of course, as David says, is another word for death. Otherwise, we're going to continue to be confronted by problems, ever more interesting problems. When we solve problems, we find more interesting problems arising from the solutions. That's the ongoing, infinite part of science, and especially physics. I've been talking to people working at the foundations of quantum theory, open questions. People working at the frontier of quantum computation, open questions. People working in various disparate areas of astronomy, from cosmology, open questions. The formation of galaxies, open questions. The formation of the solar system, open questions. How stars actually work when they've got high or low metallicity, open questions. Unanswered questions with the Big Bang are really interesting. I remember going to a talk with Roger Penrose, who has this wonderful idea. It's a Hindu cosmology almost, that he mathematically figures out that towards the end of the universe, if the universe keeps on expanding, that's the current best theory seems to suggest, the universe will keep on expanding at an accelerating rate. We're going to talk about that a little bit more today. That eventually, not only do all galaxies fly apart and the material within the galaxies fly apart, but all matter flies apart, and eventually all you're left with is a completely and utterly featureless universe of photons. They're the only things that then exist in that universe, trillions and trillions and trillions of years hence. And at that point, the universe cannot keep time in the regular way, because to keep time you need a clock, and in such a universe in the far distant future, there is no such material out of which the universe can keep a record of its own time, its own age. And so it kind of forgets, in Roger Penrose's words, exactly how old it is. So it may as well be the beginning of the universe again. And so maybe that's how a Big Bang comes about all over again. The end of the universe is a mirror image of the very beginning of the universe. And this is kind of this Hindu idea of cyclical universes. Anyway, that could be mere metaphysical, mathematical musings, but we still don't know what went on a certain fraction of a second after the instant in time at which time and space was created. What was going on? What was the thing that precipitated the origins of the universe? We don't know. This is an open question. This is probably always going to remain an open question. We'll just keep pushing it back a little bit further in time. Perhaps seeing a time before time. Who knows? But even then, we will still ask what caused that thing to happen. And again, this is just fundamental cosmology. We have unanswered questions in every area of science. But let's go to the beginning of infinity, where I'm up to the point where David is talking directly about cosmology. And he writes, quote, "In cosmology, there has been revolutionary progress even in the few years since the end of science was written, and also since I wrote The Fabric of Reality soon afterwards. At the time, all viable cosmological theories had the expansion of the universe gradually slowing down due to gravity, ever since the initial explosion at the Big Bang and forever in the future. Cosmologists were trying to determine whether, despite slowing down, its expansion rate was sufficient to make the universe expand forever, like a projectile that has exceeded escape velocity, or whether it would eventually recollapse in a big crunch. Those were believed to be the only two possibilities. I discussed them in The Fabric of Reality because they were relevant to the question, is there a bound on the number of computational steps that a computer can execute during the lifetime of the universe? If there is, then physics will also impose a bound on the amount of knowledge that can be created, knowledge creation being a form of computation." Just quickly pausing there, going back, very last phrase there, knowledge creation being a form of computation. The sine qua non, the essential part of what a human is without being an essentialist, the essential part of being of what a person is, our explanation for what a person is a knowledge creator. In particular, an explanation creator, an explanatory knowledge creator. That's the best explanation that we've had. This is the answer to the age-old question, what is a person? At least it is a lot of progress beyond anything that has come before. Is a person a creature that's able to understand morality? Is a person a creature that has a soul? Is a person a creature that is able to do mathematics and art? These were all circling the true, best explanation that we now have, which is that people are universal knowledge creators. And what David says there is just so important. Knowledge creation being a form of computation. I think a few of us have said over the years, the mind is performing computations. Get over it. It's not an analogy. We know now about the universality of computation. All physical systems out there can be modeled by a universal computer, and that includes minds. I won't go into it again now, but here we have it again in clear black and white, knowledge creation being a form of computation. We can come to understand that better, but those are the facts. Let's keep on going. Quote, "Everyone's first thought was that unbounded knowledge creation is possible only in a universe that does not recollapse. However, on analysis, it turned out that the reverse is true. In universes that expand forever, the inhabitants would run out of energy, but the cosmologist Frank Tipler discovered that in certain types of recollapsing universes, the Big Crunch singularity is suitable for performing the faster and faster trick that we used in Infinity Hotel. An infinite sequence of computational steps could be executed in a finite time before the singularity, powered by the ever-increasing tidal effects of the gravitational collapse itself. To the inhabitants, who would eventually have to upload their personalities into computers made of something like pure tides, the universe would last forever because they would be thinking faster and faster without limit as it collapsed, and storing their memories in ever smaller volumes so that access times could be reduced without limit. Tipler called such universes omega point universes. At the time, the observational evidence was consistent with the real universe being of that type." Pausing there, my reflection. I'm sort of smiling as I read that because this is one of those areas of theoretical physics that it's fun. It's lots of fun, but always in the back of my mind, I think, well, what we're talking about here is literally at least, at the time this was written, at least some billions of years hence. And these days we're thinking more like trillions of years hence when we talk about the ultimate ends of the universe, whatever that might mean. And we don't know what knowledge is going to be created tomorrow. or the next day to overturn theories like this. So when we're making these grand predictions about such vastly distant times, it kind of is like science fiction, because we just don't know what errors have been assumed within the theory here. So fun as it is, I mean, every single one of these theories suffers from the same flaw, that it cannot possibly be refuted by anyone alive today. This is what Jaron Lanier says. Well, if not anyone alive today, it cannot possibly be refuted by anyone doing an experiment within the next few billion years. Okay, so all of them can be on the table. I guess they can be refuted by other observations that we make, but this is the point about making, prophecies about the far distant future. They're just fun. They're fun to play with physically, mathematically, I guess. As David says in the very next paragraph, quote, "A small part of the revolution that is currently overtaking cosmology is that the omega point models have been ruled out by observation. Evidence, including a remarkable series of studies of supernovae in distant galaxies, has forced cosmologists to the unexpected conclusion that the universe not only will expand forever, but has been expanding at an accelerating rate. Something has been counteracting its gravity." Pausing there. So this is one of the ways that we now talk about a precision cosmology, which is exciting for those of us who kind of studied this, because, at the very beginning of my interest in this, cosmology, well, we had an understanding of the Big Bang, but that was about it. I mean, talking about the grander scales of the universe was still somewhat approaching the metaphysical. What would really happen to the end of the universe? It was very difficult to gather the data needed to be able to constrain the various competing theories. But now we can. And this particular event, this particular discovery of the accelerating expansion of the universe is burned into my own mind anyway, because I remember it quite clearly being talked about, the buzz that arose at the university in the astronomy department at the University of New South Wales, where I was, about 1998, 1999, because prior to, everyone sort of had an idea, as David just said, of what should have happened after the Big Bang, namely the slowing down of the expansion of the universe. And so what happened in 98 and 99? Well, there were two competing groups, researchers, that were working on high redshift supernovas that occurred in galaxies very, very distant from our own. And why were they looking for these things at all? Well, to constrain these models, to figure out what was going to happen to the universe in the far distant future. The thing about these kinds of supernova, there's supernova 1A. And supernova 1A are these very rare kind of supernovae where you have some kind of large star, maybe a red giant, in mutual orbit with a white dwarf star, which is much smaller. And the white dwarf stars have an upper limit on their mass. Once you exceed that upper limit, which is called the Chandrasekhar limit, the Chandrasekhar limit being named after the physicist who calculated it, I think it's 1.38 times the mass of the sun. Once the white dwarf star exceeds that number, 1.38 times the mass of the sun, then the repulsion forces of the electrons that are holding the star up, so in other words, you've got atoms buttressed up against other atoms, and the electrons are the only thing, the electron repulsion is the only thing preventing it from collapsing still further. I suppose the quantum physicists would pick me up on that and say, well, it's the Pauli exclusion principle or something like that. But whatever the case, you've got one force outwards trying to prevent the collapse and gravity inwards trying to cause the collapse. Once you exceed the 1.38, gravity wins, and there is a very sudden collapse of that star. Via complicated processes we don't need to go into, that then results in a massive explosion, basically because the entire star heats up very, very, very quickly. Now, this happens at precisely that 1.38 times the mass of the sun. It can be calculated very precisely. And so as one star, the white dwarf, is accreting, collecting matter from that other larger star, it passes that limit and explodes, and these things all explode at the same time. Now, these are very rare. So within our own galaxy, we're not going to see one more than likely, okay? These are so rare that I'm not even sure that we've ever seen one within our galaxy. I think even the supernovae that have hitherto been seen by the unaided human eye that have occurred within the Milky Way weren't even of this sort. So they're exceedingly rare. So how on earth are these researchers studying these supernovae actually able to see any? And in fact, they did see quite a number of them. And these days, you can see them daily. How is that possible? Well, rare as they are, galaxies are just so numerous that even if they only happen on average once every million years to a galaxy, well, there are trillions of galaxies out there, well, hundreds of billions that we can actually observe. And so if you have the right technology and the right computers, and you're scanning large portions of the sky, then you will pick these things up. And this is what these two competing groups of astronomers did. One of the groups was the High Z Supernovae project led by Brian Schmidt, who's an Australian. Well, at least we count him as an Australian because he won the Nobel Prize for this, but actually he was born in America, naturalised to be an Australian. He led one group, a very large group of astronomers actually, and they were competing against the Supernova Cosmology project led by Saul Perlmutter. And both of them were doing basically the same thing, making observations of these supernovae, competing in a friendly way, because I think sometimes when cloud cover obscured the view of the telescopes for one team, the other team would pick up the slack for them. So they really did work well together. And they knew what to expect to some extent from the results. And what they expected was completely unlike what the results were. And so this was a classic experiment of a kind, because it's an experiment that disagrees with the known theory, the best known theory. And there is no explanation for what is going on. So what was the problem? Just in very brief, what the problem was when they looked at these supernovae, at the distances they were, at the redshifts that they were, using redshift analysis. In other words, you collect the light and then you break up the light into what it's made out of. And what it's made out of is called its spectra. The spectra is a consequence of the kind of elements that are in the explosion of the supernova. And so if you burn copper, you get this kind of characteristic bluey-green flame. And if you burn iron, you get a red flame. If you get a carbon, you get this characteristic yellow flame. Well, the same sort of thing happens with stellar spectra. And so you collect the light with a telescope and then you put it through this thing called the spectroscope, which then goes into a computer. And it tells you what the star is made out of. That's the first thing. And the second thing is that you can figure out the redshift, which tells you how far away the star is. The problem is, once they did that and found out how far away the star was using the stellar spectra, the luminosity, the brightness of these high redshift type 1a supernova were too dim. They were not luminous enough. But the thing is, the understanding of the astrophysics of the luminosity of type 1a supernova says that it should be extremely reliable, an extremely good standard candle, something that has a fixed luminosity, no matter what the distance is or anything like that. Now, many of us did question the results at first because of things like, well, the metallicity. In other words, how much metal, how much material that is heavier than helium in the very distant universe would have been different. Because in the very distant universe, you're talking about the universe when it was much, much, much younger. And when the universe was much, much, much younger, it hadn't yet had the time to produce stars that contained within them these same kind of elements that we find in our local universe. In other words, what the sun is made out of, or what the other stars within the Milky Way galaxy is made out of. Okay, these have higher amounts of metal. Why? Because the stars have exploded, and during the explosion they release the material that's inside of them, which includes the metals. So that the next generation of stars then collects up that material and can then burn using that material. And when you look at those stars, you can see the material in it contains metals. Now, these very, very distant type 1a supernovas are happening with stars that have appeared much, much, much earlier in the universe. The light is much, much older, which means it was produced so many billions of years earlier. So maybe, just maybe, the physics of what's going on there, not the physical laws, but what's happening with the kind of material out of which those supernovas are created, maybe that's a little bit different to what is happening here, closer to us. Now, that could be the case. It still could be the case. Who knows? And that would be called a systematic error, a thing that we don't understand about the astrophysics of stars, and in particular type 1a supernovas. Maybe more distant type 1a supernovas behave differently to closer supernovas. But we can rule that out now because there's a lot of other evidence also pointing out an accelerating expansion of the universe, not least of which is the cosmic microwave background radiation analysis as well, which clever astrophysicists can figure out looking at the anisotropies and how large those anisotropies are and so on, to explain those in terms of an accelerating expansion of the universe as well. So it's not only the type 1a supernova data that we're relying on right now. And as Saul Perlmutter himself says in an article that he wrote, those high redshift supernova are fainter than we would expect, even if the universe was completely empty. So the mathematical models are strongly in agreement with the idea, the hypothesis, that the universe is accelerating in its expansion for reasons that we have next to no clue about. And as David says, let's go back to the book. He writes, quote, "Something has been counteracting its gravity, the gravity of the universe. We do not know what. Pending the discovery of a good explanation, the unknown cause has been named dark energy. There are several proposals for what it might be, including effects that merely give the appearance of acceleration. But the best working hypothesis at present is that in the equations for gravity, there is an additional term of a form first mooted by Einstein in 1915 and then dropped because he realized that his explanation for it was bad. It was proposed again in the 1980s as a possible effect of quantum field theory, but again, there is no theory of the physical meaning of such a term that is good enough to predict, for instance, its magnitude. The problem of the nature and effects of dark energy is no minor detail, nor does anything about it suggest a perpetually unfathomable mystery. So much for cosmology being a fundamentally completed science. Depending on what dark energy turns out to be, it may well be possible to harness it in the distant future to provide energy for knowledge creation to continue forever. Because this energy would have to be collected over ever greater distances, the computation would have to become ever slower. In a mirror image of what would happen in omega point cosmologies, the inhabitants of the universe would notice no slowdown because, again, they would be instantiated as computer programs whose total number of steps would be unbounded. Thus, dark energy, which has ruled out one scenario for the unlimited growth of knowledge, would provide the literal driving force of another. The new cosmological models describe universes that are infinite in their spatial dimensions. Because the Big Bang happened a finite time ago, and because of the finiteness of the speed of light, we shall only ever see a finite portion of infinite space. But that portion will continue to grow forever. Thus, eventually, ever more unlikely phenomena will come into view. When the total volume that we can see is 1,000,000 times larger than it is now, we shall see things that have a probability of 1 in 1,000,000 of existing in space as we see it today. Everything physically possible will eventually be revealed. Watches that come into existence spontaneously. Asteroids that happen to be good likenesses of William Paley. Everything. According to the prevailing theory, all those things exist today, but many times too far away for light to have reached us from them yet. Pausing there, my reflection. So this is on the assumption that everything that physically possibly can happen indeed will happen, which is one way of understanding, for example, the multiverse. Could be one way of understanding the universe like ours. This assumes, of course, this argument that David has just made there about watches popping into existence and good likenesses for William Paley, assumes the cosmological principle. The cosmological principle being, on very large scales, the universe is homogeneous and isotropic. Homogeneous being, it's the same at every single point. It looks the same at every single point. And this is an assumption. I don't know that it's something we can derive from more fundamental theories of physics. I think we just assume it logically needs to be the case. And so then this would follow. Constructor theory, of course, may have some new light to shed upon things like this. And the idea that anything that can happen indeed will happen. Now, everything might happen just by chance. That's one thing. But then some things might need to be made to happen, even though they're possible. We might need a constructor for it. And for more on that, you'll have to go to my series on the physics of Can and Can't. And before that, buy the book, The Physics of Can and Can't by Chiara Marletto. But for now, let's go back to the cosmology here. David writes, light becomes fainter as it spreads out. There are fewer photons per unit area. That means that ever larger telescopes are needed to detect a given object at ever larger distances. So there may be a limit to how distant and therefore how unlikely a phenomenon we shall ever be able to see. Except that is, for one type of phenomenon, a beginning of infinity. Specifically, any civilization that is colonizing the universe in an unbounded way will eventually reach our location. Hence, a single infinite space could play the role of the infinitely many universes postulated by anthropic explanations of the fine-tuning coincidences. In some ways, it could play that role better. If the probability that such a civilization could form is not zero, there must be infinitely many such civilizations in space, and they will eventually encounter each other. If they could estimate that probability from theory, they could test the anthropic explanation. Furthermore, anthropic arguments could not only dispense with all those parallel universes, they could dispense with the variant laws of physics too. Just pausing there, David does have a note here that when he says those parallel universes, he's talking about universes with different physical laws. This is not the quantum multiverse. Completely different. Completely different. Remember, the multiverse in the quantum theory explanation is a multiverse where all the universes are obeying exactly the same laws, namely the laws of quantum theory. But there's this kind of megaverse idea used in anthropic arguments where we have the concept of universes with different physical laws. And as I say, I was speaking to a researcher today who does simulations of this kind of thing, and has very interesting ideas about, for example, fiddling with the knobs of the constants of nature. So, for example, the gravitational constant G, the fine structure constant, the cosmological constant, these things, you can fiddle with the values of these things and then see what happens to the universe. And most fiddlings of the constants result in featureless universes. Some, he was saying, don't cause the extinguishing of life very easily, but some do. Cosmological constant, gravitational constant, for example, have huge effects on either formation of galaxies or formation of stars. Now, the interesting thing there, which I wasn't aware of, because I know these simulations are done, simulating entire universes with different laws in a sense, namely the values of the constants are different, but keeping everything else the same. What the researchers cannot yet do, which I asked about, can you simulate universes with entirely different laws of physics, in the sense that, well, let's not have general relativity. Let's have something completely different. Let's not have quantum theory. Let's have something completely different. This is not possible at the moment. It's not feasible at all. He was saying, well, if you wanted to change the law of gravity, then you would need to redo stellar physics, stellar nucleosynthesis, for example, using that new theory. So that's a whole other thing that the simulation would need to be able to cope with. So they're not even there. The best they can do now, clearly this is really just merely scratching the surface of trying to figure out, could life exist in universes with different physical laws? All they're doing is fiddling with the constants of nature and keeping everything else exactly the same. In other words, the laws of physics have exactly the same form. It's just the coupling constants are different. And so they're getting interesting results out of that. The interesting result is almost all choices, other than the selection of constants that we do have, result in a sterile universe. That's an interesting enough result. But it's certainly not putting paid to this idea that if there is a megaverse out there, there could be infinite civilizations out there. There could be. I don't believe this. I don't think anyone should believe this. No one knows this. It's just completely conjectural right now. We have no way of constraining any of these theories, really. We don't have an answer to the fine-tuning problem. This is why we're very much at the beginning of infinity as far as this question is concerned. Okay, so I'm skipping a bit that David writes here. You'll have to go to the book yourself to read that bit. And I'll skip to where he talks about the Fermi problem. So he's just finished describing some aspects of the issue with fine-tuning and with purported solutions to fine-tuning, and namely the anthropic argument. And of the anthropic argument, he says, quote, "Nor therefore can it solve the Fermi problem. Where are they? It may turn out to be a necessary part of the explanation, but it can never explain anything by itself. Also, as I have explained in Chapter 8, any theory involving an anthropic argument must provide a measure for defining probabilities in an infinite set of things. It is unknown how to do that in the spatially infinite universe that cosmologists currently believe we're in. That issue has a wider scope. For example, there is the so-called quantum suicide argument in regard to the multiverse. So suppose you want to win the lottery. You buy a ticket and set up a machine that will automatically kill you in your sleep if you lose. Then in all the histories in which you do wake up, you are a winner. If you do not have loved ones to mourn you, or other reasons to prefer that most histories not be affected by your premature death, you have arranged to get something for nothing with what proponents of this argument call subjective certainty. However, that way of applying probabilities does not follow directly from quantum theory, as the usual one does. It requires an additional assumption, namely that when making decisions, one should ignore the histories in which the decision maker is absent. This is closely related to anthropic arguments. Again, the theory of probability for such cases is not well understood, but my guess is the assumption is false. Pausing there in my reflection. Yes, so this quantum suicide idea that if you commit suicide, you should expect as a matter of probability within the multiverse that you'll wake up tomorrow. My way of understanding this is, no, a version of you will wake up, but that's not you. We've talked about this before, and I did recently an episode called The Nexus, which is where I think that the strands of the fabric of reality, everything that's in the beginning of infinity really, brought together really provide the best explanation for what a person is, and that's why I call it the nexus. This mixing of the threads of the fabric of reality give us a better understanding of what a person is. And in that, I was trying to understand the nature of personhood in the context of the multiverse, knowing that we consist of infinitely many fungible instances right now. So sitting here right now, continuing to speak to you, are many fungible instances of myself. And right now, some portion of them, some measure of them, have gone off to get a cup of tea and do a variety of other things as well. But there remains a set of fungible instances right here. Now, I'm not conscious of those other versions, right? There are other versions of me that have gone. Now, if I arrange to have myself killed in my sleep, how does consciousness deal with that? Are you extinguishing a particular consciousness forever and for good and allowing another one to wake up? There's no guarantee that it's you. And this is why David says you can't ignore the histories in which the decision maker is absent. Okay, so something has been killed. We know, as a matter of fact, that people die in our universe all the time. We can see them dying. Now, some versions of them then go on to exist. All right, but we're not observing those. Why should you think that you're going to be the observer of the version that survives? There is no good argument for this. This is why I think that something will survive, possibly, given our best understanding of quantum theory now. But I'm not betting my life on it at all. I think the quantum immortality thing, quantum suicide thing, it doesn't run through. And I think all it says is that we've got a lot that we don't understand here. That's all. This is another flag, like dark energy, for a problem. It's not a solution to anything. There's not an explanation there. And so given that, we shouldn't we shouldn't go trying to play the lottery in this way. Okay, let's go back to the book, because we're about to talk about one of my favourite philosophers. David writes, a related assumption occurs in the so-called simulation argument, whose most cogent proponent is the philosopher Nick Bostrom. Its premise is that in the distant future, the whole universe as we know it is going to be simulated in computers, perhaps for scientific or historical research. Many times, perhaps infinitely many times. Therefore, virtually all instances of us are in those simulations and not in the original world. And therefore, We are almost certainly living in a simulation, so the argument goes. But is it really valid to equate most instances with near certainty like that? For an inkling of why it might not be, consider a thought experiment. Imagine that physicists discover that space is actually many-layered like puff pastry. The number of layers varies from place to place. The layers split in some places, and their contents split with them. Every layer has identical contents, though. Hence, although we do not feel it, instances of us split and merge as we move around. Suppose that in London, space has 1 million layers, while in Oxford it only has 1. I travel frequently between the two cities, and one day I wake up from having forgotten which one I am in. It is dark. Should I bet I am much more likely to be in London just because 1 million times as many instances of me ever wake up in London as in Oxford? I think not. In that situation, it is clear that counting the number of instances of oneself is no guide to the probability one ought to use in decision-making. We should be counting histories, not instances. In quantum theory, the laws of physics tell us how to count histories by measure. In the case of multiple simulations, I know of no good argument for any way of counting them. It is an open question, but I do not see why repeating the same simulation of me 1 million times should in any sense make it more likely that I am a simulation rather than the original. What if one computer uses 1 million times as many electrons as another to represent each bit of information in its memory? Am I more likely to be in the former computer than in the latter? A different issue raised by the simulation argument is this. Will the universe as we know it really be simulated often in the future? Would that not be immoral? The world as it exists today contains an enormous amount of suffering, and whoever ran such a simulation would be responsible for recreating it. Or would they? Are two identical instances of a quale the same thing as one? If so, then creating the simulation would not be immoral, no more than reading a book about past suffering is immoral. But in that case, how different do two simulations of people have to be before they count as two people for moral purposes again? Again, I know of no good answer to these questions. I suspect that they will be answered only by the explanatory theory from which AI will also follow. Pause there, my reflection on that. Yes, so David has mentioned this before all the way back I think it's in A Window on Infinity, an earlier chapter. The problem with trying to count infinities. And that if you have these universes with different physical laws, you have an uncountable infinity. And if you're thinking of this fractal type situation, where in the distant future there's going to be civilizations that will have computers in which there'll be simulations of people who have computers in which there are going to be simulations and so on and so on and so on, just fractally expanding out. There's no way of counting these, and so we don't even know what the nature of consciousness is either. And by the way, our best understanding of physical reality that we occupy right now, as we've already said, is that you are infinitely many fungible instances already, which can't be counted. And so in what sense are those more numerous than you? What if, like David's giving a hint here, if the simulated versions of you are not infinitely many fungible instances, but are based upon some other kind of simulation of the laws of physics which nevertheless allow for conscious experience? Well, we've done experiments here to show that we live in a universe that is governed by the laws of quantum theory, which mean that you as a person aren't a single instance. But maybe those simulated, the most efficient way of simulating people in those computers is single instance people. Maybe that's it. Don't know. But we know that we're not single instance people. We're uncountably infinitely many. So maybe we already outnumber even that number of infinitely many people being simulated. I wonder why, well, he wouldn't have known. Nick Bostrom didn't take into account this idea of the multiverse already, that we live in a multiverse, because not many people take the multiverse seriously enough. And analytic philosophers should. Okay, skipping a little, and let's go to a little bit more about Bostrom. And David writes here, an even more dubious example of anthropic type reasoning is the doomsday argument. It attempts to estimate the life expectancy of our species by assuming that the typical human is roughly halfway through the sequence of all humans. Hence, we should expect the total number who will ever live to be about twice the number who have lived so far. Of course, this is prophecy, and for that reason alone cannot possibly be a valid argument, but let me briefly pursue it in its own terms. First, It does not apply at all if the total number of humans is going to be infinite. For in that case, every human who ever lives will live unusually early in the sequence. So if anything, it suggests that we are at the beginning of infinity. Also, how long is a human lifetime? Illness and old age are going to be cured soon, certainly within the next few lifetimes, and technology will also be able to prevent deaths through homicide or accidents by creating backups of the states of brains, which could be uploaded into new, blank brains in identical bodies if a person should die. Once that technology exists, people will consider it considerably more foolish not to make frequent backups of themselves than they do today in regard to their computers. If nothing else, evolution alone will ensure that because those who do not back themselves up will gradually die out. So there can be only one outcome: effective immortality for the whole human population, with the present generation being one of the last that will have short lives. That being so, if our species will nevertheless have a finite lifetime, then knowing the total number of humans who will ever live provides no upper bound on that lifetime, because it cannot tell us how long the potentially immortal humans of the future will live before the prophesied catastrophe strikes. In 1993, the mathematician Werner Vinge wrote an influential essay entitled The Coming Technological Singularity, in which he estimated that within about 30 years, predicting the future of technology would become impossible, an event that is now known simply as the Singularity. Vinge associated the approaching singularity with the achievement of AI, and subsequent discussions have centered on that. I certainly hope that AI, by which David means AGI, is achieved by then, but I see no sign yet of the theoretical progress that I've argued must come first. On the other hand, I see no reason to single out AI as a mold-breaking technology. We already have billions of humans. Most advocates of the singularity believe that soon after the AGI breakthrough, superhuman minds will be constructed, and that then, as Vinge put it, the human era will be over. But my discussion of the universality of human minds rules out that possibility. Since humans are already universal explainers and constructors, they can already transcend their parochial origins, so there can be no such thing as a superhuman mind as such. There can only be further automation, allowing the existing kind of human thinking to be carried out faster and with more working memory, and delegating perspiration phases to non-AI automata. A great deal of this has already happened with computers and other machinery, as well as with the general increase in wealth, which has multiplied the number of humans who are able to spend their time thinking. This can indeed be expected to continue. For instance, there will be ever more efficient human-computer interfaces, no doubt culminating in add-ons for the brain. But tasks like internet searching will never be carried out by superfast AIs scanning billions of documents creatively for meaning, because they will not want to perform such tasks any more than humans do, nor will artificial scientists, mathematicians and philosophers ever wield concepts or arguments that humans are inherently incapable of understanding. Universality implies that in every important sense, humans and AIs will never be other than equal. Similarly, the singularity is often assumed to be a moment of unprecedented upheaval and danger, as the rate of innovation becomes too rapid for humans to cope with, but this is a parochial misconception. During the first few centuries of the Enlightenment, there has been a constant feeling that rapid and accelerating innovation is getting out of hand. But our capacity to cope with and enjoy changes in our technology, lifestyle and ethical norms and so on has been increasing too, with the weakening and extinction of some of the anti-rational memes that used to sabotage it. In future, when the rate of innovation will also increase due to the sheer increasing clock rate and throughput of brain add-ons and AI computers, then our capacity to cope with that will increase at the same rate or faster. If everyone was suddenly to think 1,000,000 times as fast, no one would feel hurried as a result. Hence, I think that the concept of the singularity as a sort of discontinuity is a mistake. Knowledge will continue to grow exponentially or even faster, and that is astounding enough. Pausing there, ending the reading there for today, because it's a wonderfully positive part to end on. This singularity, by the way, if you want some more eviscerating critique of it, I think that's as strong as you can get anywhere, but a slightly different approach to it. The computer scientist Jaron Lanier, Jaron Lanier. He is far too unknown. Okay, he's known amongst a certain community of people, but he deserves to be, like David Deutsch, far more well-known than what he is. And Jaron Lanier has an additional kind of handicap in that he doesn't like social media, and so he refused to go on social media. But you can find his wonderful talks that he gives on YouTube, and his books are absolutely brilliant. And he similarly doesn't agree with the Bostroms and the Ray Kurzweils and the Werner Vinges of the world on this point about doomsday and the singularity, and we're going to, upload ourselves to the internet and all this sort of stuff. He admits of the mystery of human consciousness, for example, in a slightly different way to David. It'd be interesting to hear them have a conversation. But here, this whole idea, the singularity, that there's going to be this sudden takeoff of technology. Well, haven't we already had that? And like David says, the psychological impact of this is, well, apart from the doomsayers, the naysayers, the pessimists that have always been with us, they complained about, the invention of the motor vehicle, or the television, or the telephone, the book. Okay, there's that great Twitter account, Pessimists Archive, where they reproduce very old newspaper articles of people complaining about things like books and how books are ruining children, ruining their lives. And then, of course, that moved on to radio is ruining children's lives, and television is ruining children's lives. And, of course, today it's not just computers, but any piece of technology is ruining children's lives. We've always had the pessimists trying to tell us that technology is bad for us, that we can't handle it. And there is this zeitgeist now that people aren't handling the technology particularly well. But, with every solution comes new problems. Would you rather be out in the field scratching the existence out of the dirt as, Neanderthal people used to do? Of course not. Okay, we have some problems with technology today, but they're a heck of a lot better than the dealing with the problems that they solved. Also mentioned there is you can't have AI being super intelligent and taking over all of our tasks, especially not the creative ones, because they'll be people. Super intelligent, narrow AI, AI that's super intelligent in the sense that it can beat us at chess, never wants to choose to do anything other than chess. And so it's not a threat to us. For more on this, see my articles at bretthall.org about superintelligence, where I critique Nick Bostrom's view of superintelligence, his book, Superintelligence. I think it's... I was disappointed in it more than the fact I didn't like it. In a sense, I kind of liked it because it read like a science fiction book. And I listened to the audio, and whoever reads the audio, they sound a bit like a robot, so it's a little bit scary. But they're in that uncanny valley where they're human, but just a little bit like Nick Bostrom to some extent. That's very cruel. No, Nick Bostrom's obviously extremely intelligent, but the book for me was disappointing because I was expecting to be blown away by the precision of the philosophy, but in fact it was the philosophy and the epistemology that was the weakest part of the book, and it was upon this foundation that rested all the pessimism. So once you get the epistemology wrong, the pessimism just flows naturally from these ridiculous ideas about how Bayesianism, and this is what really turned me off Bayesianism, I think it was. So I have to credit Nick Bostrom for inspiring me to really research the depth of Bayesianism and realizing the poverty of the epistemology at the heart of what Bayesianism is all about. And so if you just take on Popper's conception of epistemology, you don't get these pessimistic ideas about AI and doomsday and so on and so forth. It's no accident that the pessimists are prophets with bad epistemology. It's an awful trinity of misconceptions that go together there to all self-support one another. Just take on the right epistemology, and you'll no longer be tempted to make prophecies. Okay, you will admit of your ignorance on the one hand, and then realize that there's hope for the future in being able to solve any problem using creativity. Okay. Next time will be, sadly, to some extent, the final episode on the beginning of infinity. I'll probably do that from somewhere else, a slightly nicer, different location. I think I'll have to think of ways in which I can make the final episode something different, something great. Okay, but until then, bye-bye.